name is Fuguang Shi. I'm from Juniper Networks and now part of HPE. So today's topic, we're talking about network ASIC architecture basic review as well as some case studies. So the agenda I'm going to cover is a basic architecture review, and that will include packet processing architecture and also buffer architectures. And I'm also going to talk about network ASIC trends, including landscape and some case studies. So here's a quick review of network ASIC architecture. Following slide, we'll do a quick review, and this had been talked at NetNoc 93 by my colleague Nancy Shah. And here's a link to her presentation and videos. So first thing, in network ASIC, where is it in a system? So in the diagram here, I'm showing is a chassis system. And the picture here showing is a 8-slot line card chassis. And each line card is connected by a fabric card, which usually at the back of the chassis. And each line card can have a multiple network ASIC, and of course usually have its own CPU on board to manage all the ASICs. And front panel usually is just Ethernet port in today's system. So another form factor is a standalone box. So it's a kind of, some people also call it fixed form factor. And it's not the modular chassis, it's basically, some people also call it pizza box. And it can have multiple ASIC inside and connect by fabric, or can only have single ASIC. So for example, in today's new box, single chip can reach up to 28.8 terabit, which if you look at the front panel, we can have 36 Ethernet port, which each port can be up to 800 gig, and form a 28.8 terabit single box with a single chip solution. So which usually give us the most power efficiency and as well as the density. So now let's talk about packet processing architecture. So there's two main architecture I'm going to talk about or review. One is multiple packet processing engine architecture on the left-hand side of the diagram. And basically, the packet process engine is doing all the packet processing work. And within a chip, we can put a lot of those, depending on the capacity we want to build. It could be put 64 such engine, 128, or 256. And each packet processing engine is fully programmable, so make it very flexible to do the packet processing. So another architecture we developed is pipeline architecture. So basically each processing box and formed in a pipeline fashion, and each one doing a limited job, but doing only this job. So usually have a lower latency and high performance. So let's compare the pros and cons of these two architectures. Multiple PPEs, so because it's a fully programmable, so it can support all different features. And feature even can be added later on, even the product is released. So by releasing a new OS, you can get a new feature as well. And you get the highest level of flexibility. And each PPE can access a fungible memory. The drawback, the cost per bit or power per bit usually will be higher than pipeline architecture. So on the pipeline architecture, usually it has a higher performance, which means higher speed, lower power, and typically lower latency than multiple PPE architecture. And it covers most of the major use cases. Of course, the drawback, it cannot reach the flexibility of the multiple PPEs that architecture offers. So another important architecture inside the silicon is the buffer architectures. So buffer basically provide packet storage during period of transient congestion. And queue basically store packets according to priority or quality of service. And there's the two main different architecture choice. One so-called two-stage buffering. Basically, the packet will be stored in the ingress and stored again on the egress. And another buffering structure, which on the right-hand side of the diagram, is we only store the packet on the ingress. And the buffer here I draw is pretty much the deep buffering I'm referring to. So some silicon has a shallow buffer. Pretty much there's no external memory. It's all on-chip memory. So let's take a quick look of the two-stage buffering architecture. So basically, packet gets buffered first on ingress to be scheduled across the fabric. The green bar on the middle is the fabric. And usually it requires a lower number of the queues because only need to know which destination PFE will send to. And packets gets buffered a second time on egress port to be scheduled out on the local port. So, which means on egress side, the memory can be all used for its local port. So it can have a large number of queues, and because all queues are only used for local egress port. And for a total system queue number, usually the more line card, the more ASIC, basically you have more queues. So total queue number usually equals to number of the line card you have, and number of ASIC on each line card, and how many queues per ASIC. So another architecture is ingress-only buffering, VOQ system. So VOQ here is the virtual output queue. The main advantage of VOQ system is no header line blocking. So I have a diagram here. So in the case of we have 4 egress ports defined in this system, such as egress 000, and egress 050051. And assume each egress port will support 8 queues. So for the ingress buffering, we need to store all those 4 ports, 8 queue information on the same buffer. And this buffer, each PFE will have to duplicate on each one. So they're no longer a multiple factor in this kind of system. Basically, all will be buffered in this deep buffer here. So let's do a quick comparison between the two buffer architectures. So two-stage buffering, and we can support many more queues per egress port. So which is very good for support complex subscriber and QoS management. And there's no head of line. Two-stage buffer, there's a potential head of line blocking. There's somehow misaligned on this one. So there's a potential head of line blocking, and packet need to read-write external memory twice because it will be write when on the ingress side and rewrite again on the egress side. On ingress only single-stage buffer, there's no head of line blocking, and packet read to external memory only once in the system. And usually the drawback is lower scaling queue numbers. So what is the industry trend and the market segment with current different architectures? First, so bandwidth continue to grow, and we don't see the end. Even actually in recent years, maybe accelerate even more. So AI is the main force today to drive some key technology for networking. And there's an increased network specialization with different equipment requirements, and which also leads to network silicon domain segmentation. So here, let me just try to get everything in one page. So we roughly partition at edge routing, core routing, and data center switching. And on each bar, we try to look at the larger scale. Large scale usually means tunnel numbering, how many FIB we can support, and packet buffers, and also header processing capability, and single chip bandwidth. And you can see from edge routing usually require higher, larger scale, and requires more packet buffer, requires more header processing power, and usually single chip bandwidth is relatively lower, just compared to this. And on the other side, on the other end, if the data center switching on some, maybe just enterprise switching, and larger scale will be lower, and packet buffer requirement is less, and header processing is less, and single chip bandwidth usually is very high. So here I put the few silicons, which is, I think, the industry well-known one. On the Trill, which is the Juniper's MX series, based on the Trill silicon. And usually it's covered very well on the edge routing segment. And Juniper's Express silicon product line can cover well some of the edge and also core routing. And on data center switch, usually they don't need a deep buffer. So the Tomahawk or Trident, which from Broadcom, will be covered this marketing very well. So I put a comparison, say Broadcom has a Jericho chip, Tomahawk, and Trident. And Cisco has Silicon One. And Nokia have FP5, which try to cover different market segments. So give an overview on this. So if we map those chips into different architecture in terms of packet processing, so Juniper Trill architecture is more on multiple PPE architecture, and similar as a Nokia FP5. And on the pipeline architecture, Juniper Express architecture, Cisco Silicon One, and Broadcom Jericho family. I didn't put Tomahawk. Tomahawk should belong to this category, but usually it's not a deep buffer chip. It's a shallow buffer chip. Basically, there's no external memory. So I borrowed this slide from our marketing team. So basically, it's trying to color code it with different market segment and what architecture serves those are better. And in the middle is the service provider, content provider, application provider. And usually, those in purple color, pipeline architecture serves this market fairly well, provide pretty good cost per bit or power per bit. But for the service edge, which requires a lot of features or maybe a lot of queues, then the PPE architecture serves those markets very well. And on the end, or right side, the end of the data center, which is the white colored, typically for example, the shallow buffer silicon get a better cost per bit or power per bit. So I talk about AI is the main driving force today to kind of drive the network evolution. So there's a talk about scale out and also scale up and scale out. The key to connecting today's GPU try to be, and there's a new requirement coming into the picture. One is requires lower latency. They really require very low latency. The second is try to build a lossless connection or network. So industry has formed some consortium, try to develop some schemes, such as link layer retry. So if your service has an error, instead of that software layer to know, hardware layer will just retry the packet which gets lost. And also develop some kind of flow control mechanism, like priority flow control or credit-based flow control. So which try to solve the problem if there's any congestion caused by packet loss, we use the flow control to make sure there's no packet loss. So now if you choose what kind of architecture to serve what market, we really need to think about whether we choose multiple packet processing engine or versus pipeline architecture. And whether we need to use two-stage buffering or ingress-only VOQ system. And also, even the ingress-only VOQ system, we're talking about whether we want to have a deep buffer with external DRAM. Today, mostly is HBM, and versus shallow buffer without external DRAM. And of course, there's also new emerging silicon technologies who are affecting the architecture choice, such as, for example, foundry nodes. In today's, we tip out silicon mostly is in 3 nanometers, but it quickly will move to 2 nanometers, and will be sooner enough will be 1.4 nanometers. So if you attend the TSMC symposium, they will give a roadmap where the geometry goes. And second is new 2.5D and 3D package technology, and such as like a CoWoS, chip on wafer on substrate. So allow us to put a multiple die connect together and within a single package. And there's a new topic also talk about the co-packaged optics. Industry has a different view on this, and some companies think this is the way to go. I think it's a good technology if we can pull this through. So now I'm going to give some case studies here. So we talk about express ASIC evolution. So we start building this express silicon at around 2012. So you can tell the capacity of a chip is around 120 gig per chip. And use those chips, we can build a line card, which is around 1 terabit per line card. And into the next generation, we kind of integrate a lot together. So basically, single chip performance improved to 500 gig per chip. And line card capacity increased to 3 terabit per line card. And we started to build the fixed form factor as well at that time. Fixed form is a 3 terabit unit, basically. So even fixed form factor, we have a 6 chip inside. And of course, the fabric chip connect them together. And also, we add a lot of new features. Along the evolution, there's a new feature will be added. And in the third generation, it becomes 1 terabit per chip. And on the line card, it can be 8 terabit per line card. And we build a 16 terabit fixed form factor system as well, based on this silicon. And on Express 4, which is 3.6 terabit per chip, and line card is 14.4 per slot. And we have a fixed form factor, which is 9.6 terabit. And then latest in production is 28.8 terabit per single chip. So I have a real silicon picture here. So middle die, there's a 2 PFE die, and there's a 4 HBM die, and there's another 4 is just dummy die for mechanical reason. So these 2 die, put them together through the interposer, and they all packaged within the same package. So this is the one goes to single chip can power a fixed form factor with 28.8T. And of course, we are building the next gen, which will, performance will be at 57.6 tera per bit. And Ethernet will be support 1.6 T per port. So on the feature side, you can tell, for example, gradually we add new features. Starting from Express 3, we add MACsec support at the line rate. So basically, each generation, we actually need to redesign the MACsec to support line rate. In today's, meaning where we support 1.6 terabit line rate at any packet size. Now, let me talk about the Trail ASIC evolutions. So we developed Trail ASIC around 2009. And the first generation is 70 gigabit per second-ish. You can tell how different of today compared to then. And the second generation is around 130 gig. And pretty much each generation either double the performance, most likely, and sometimes because may not be exactly double. But Trail series is fully programmable packet processing architecture. So also if you compare, let me finish this slide first. So today's, we have Trail 7 in the lab, which is a 3.2 T, and which support 800 gig E. And you can see the Q number is really high. We can support 512K Qs. And of course, a lot of other features. We support PTP and all those functionalities. So if you compare the Trail ASIC, even today's, the most advanced we are building is 3.2 T. But if you compare back to the Express, which is a pipelining architecture, we're talking about 57.6 T. So there's a big gap between in terms of performance. But the Trail system, because of its fully programmable, it's very suitable for a lot of new features. If your device talking a lot of legacy device, for example, use some legacy protocol you need to support, and all those even future protocols. So it all can handle with this chip. So, okay, last slide, I put the Broadcom Tomahawk chip here as well as a comparison. So Broadcom Tomahawk chip is basically a shallow buffer chip. So if you look at, let me show you the Express. One more. Okay, so in the Express 5, you can see the main die is in the middle, and the side small die actually is the HBM memory. So which is usually is a deep buffer. Deep buffer, of course, serve to store the, you can provide much bigger delay bandwidth buffering, and also can provide, for example, the scale of the FIB, the scale of the counter. All those can be much bigger you can store in the external memory. But the problem is also the interface will occupy the die area around this area. So typically you don't have enough space to put the SerDes around those areas. So then typically you will see deep buffer silicon performance usually mostly is almost half of the shallow buffer silicon. So if you can get away with shallow buffer, yeah, sure, go ahead. Shallow buffer will provide even better cost per bit or power per bit. So Tomahawk basically is in that category, which is a shallow buffer silicon. They don't provide the external memory. So if you can manage, just use it on chip memory, and that probably is a very good one. So in terms of, so Tomahawk the first Tomahawk was released on 2014. So if you look at the timeline, still Trill start 2009 and Express start 2012, and this is 2014. But they also from Tomahawk 1 to today's Tomahawk 6. So if you look at the max bandwidth, the first chip is 3.2 T. Today, they actually can reach up to 102 terabit per second per single chip. Of course, this chip is also a chiplet design. It's not a single die, it's a multiple die. So they can have a peripheral die on the SerDes on a separate die and then the PFE on a different die. And if you're looking at the process node, first Tomahawk is 28 nanometers, today is 3 nanometers. And same for Express 6, as well as the Trill 7, it's all 3 nanometer chips. And if you look at the SerDes speed, we have 25 gig at the Tomahawk 1, and today, SerDes speed is about 100 gig or 200 gig, they support both. I think Express 6 also support 200 gig SerDes. So, and of course, Tomahawk 5, and also pretty recent, it's like a 51.2 terabit per second. I believe the recent release also, they're called Tomahawk Ultra. So Tomahawk Ultra is very low latency. So that, and also designing some flow control mechanism and link retry schemes. So we try to address how to connect the GPU, thousands of GPU with a very low latency and also reliable lossless connectivities. So that basically concludes my talk today. Thank you.
All right, thank you, Fuguang. That was an excellent talk. Are there any questions? We have a couple of minutes. I think I see one here. Just remember to say your name and company you're with and ask away.
Hi, Fuguang. Good to see you after yesterday, after the Behringer. Jared Cordova with Nokia. I was curious on the difference between the Trio 6 and the Express 5, if they both use the 2.5D HBM packaging, or if the Express 5 uses the 3, because there was something in the slides about the 3. So
They are the same packaging technology.
okay, is there a reason why they use the same one, or just curious? Because they're different, so I was just curious if there is a reason why you mentioned the 3. So I was just curious on that.
So you are talking about Express 5 versus Trill 6, right?
Yeah.
Yeah, it is different technology vendor, but the packaging is pretty much still on interposer, connect the main die to HBM.
Okay.
Yeah.
Thanks.
Okay, any other questions? All right, thank you.
Thank you.